Hello and welcome to Built Environment Matters, a monthly podcast brought to you by Bryden, an international company of technologists, designers, architects, engineers and analysts working for a better built environment. Bryden believe in design to value, to cut carbon, drive efficiency, save time, make beautiful places and build a better future.
Hello all, and thanks for joining this edition of Built Environment Matters, the Bryden podcast. I'm your host, Jaimie Johnston. I'm Head of Global Systems at Bryden, and today I'm joined by Pablo Gugel, who's our Head of Sustainability.
Hi, Jaimie. How are you?
Hi, Pablo. Yeah, great. Thanks for joining. So let's kick off. Can you give us a bit of an intro to yourself, your background, and how you came to join Bryden?
Yes, I'm an architect educated in Spain, and I moved to the UK, I think, like 13 or 14 years ago. And I worked for a couple of years as an architect in Greenshaw, who's an old friend of Bryden. And then I started a master in sustainable environmental design, which is what changes everything from an architectural career into sustainability. And that led me to teaching. I've been teaching at the UCL Architecture Association and Royal College of Arts, and worked for 10 years at Chapman P-DfMA and Atelier 10 afterwards. So that basically was where I got all my technical knowledge. And then I decided to move to Bryden 6 months ago, I think it's now, more or less. The reason is because I wanted to explore new approaches. And I found that when I learned about Bryden, there's a really interesting potential connection between modern methods of construction, DfMA, and sustainability. There's a real link there that we need to exploit, and that's what we've been trying to do for the last 6 months.
Yeah, it's great. So coming from an architectural background, I suppose that inherently you're sort of taught how to think in terms of integration, how to lead a project. So that's quite an interesting way into it. So rather from an engineering background, you started as sort of architect and came into it. Perhaps you can talk a bit more about what that means to us in terms of the integration, that link, as you said, between MMC and sustainable design.
Yes, that's actually important because when I started learning a bit about sustainability, I realized that there are two languages almost. There's the architectural language and there's the engineer language. And there's like a completely different knowledge you need to have to be able to interpret both languages. So if you want to have an integrated design, which means that you have all the different subjects feeding in the same direction in a project, there's a unique opportunity in Bryden. That is that we have all the disciplines under one roof. We have architects, we have engineers, we have civil engineers and building services engineers, and we have a sustainability and building physics team. So that means that integration happens in a more natural way. You can get integrated design in normal projects where you have all the different members of a team in a room, and in those meetings, you can achieve that integration, but it is more natural and easier when you have all the disciplines in one roof. And I think the objective is to make sustainability the glue, being at the center of the conversation, so that all the different disciplines learn the language and talk about sustainability and try to push in the same direction.
Yeah, it's quite interesting because we've talked on this podcast before, I think, about translation into different languages. So yeah, you're almost saying sustainability should be the common language. If everyone talks that, then whether you're an architect or an engineer, you're sort of heading in the same direction. At least it gives you a common point of reference and a sort of common aim to achieve on every project.
I think so. I think it's important, yes, that we learn that language. And I think everything is going into the same direction. There's a lot of interest and pressure in the sustainability to make more sustainable buildings. And I think we have a very collaborative team, and I think collaboration is really important because one thing that tends to happen in sustainability is that unless you start talking about it in the early stages of design, it is really difficult to root it in the project. So what we try to do is creating an iterative process, a collaborative work, where at early stages we arrange a series of workshops with all the different specialists, and then at each RIBA stage, we do like a feedback loop. We revise the ambitions, we revise the targets, we try to push harder. And that gives a lot of very useful information. There's a lot of like a cyclical feedback that I think is important for us because we need to constantly learn. This is sustainability is a moving target, but it also adds maximum value to the client. Clients want to understand what they are doing and they want to get that kind of feedback. I think one other thing that characterizes Bryden, the sustainability and building physics team within Bryden is that we are a science-based team. We like data, we like graphics, we like to understand how things operate, and we like simulating it. And we have a wide range of technical knowledge, and that enables us to deliver all the different aspects of sustainability at a very highly technical level. So we can do from things such as operational energy and carbon, embodied carbon. We can do facade optimization, daylight, sunlight, and glare simulations. We can do things which are really specialized, such as CFD and benchmarking, which is like the umbrella of sustainability in a way. So I think we have the capability of offering integrated, collaborative, and science-based designs for projects.
So it's a field that's awash with acronyms and terms. So even in that sort of last answer, there's quite a few terms knocking around. And I think it's one of these things where perhaps people use them interchangeably, which maybe for a while was sort of, it was a direction of travel. I think now it's getting to the point where some of these things make a difference. So perhaps you can unpack some of these terms. So you've mentioned embodied carbon, net zero carbon gets talked about, passive house, building physics. Perhaps can you start with building physics, just to clarify that, and then we'll get into some of those other terms.
Yeah, I think building physics is an interesting one, because the way I see sustainability is the bigger term, and building physics is a way of doing things to service the sustainability. So building physics is basically understanding the physical concepts, the concepts, but also the maths behind how you can simulate and how you can emulate the performance of a building. And that can be calculating the energy consumption of a building over some period of time, to thermal comfort. You can simulate thermal comfort. You can simulate the daylight performance of a building, or the amount of solar radiation through a window. All of that is data. All of that is pure physics, essentially. But it's called building physics because it's the physics that relate just to how a building performs. And I think there are lots of terms, as you said. One of them that I mentioned is CFD. That's computer fluid dynamics. That's one very specific one that explains how temperatures and air movement moves within a building or around a building, or you can simulate the winds, a wind path. And that's important to us because that enables us to understand in complex geometries how temperatures move. So let's say if you design an atrium, which is a complex thing to design, what happens to the temperature at the lower level of that atrium? What happens with the temperatures at the higher level of that space? How the air moves from the adjacent rooms into that space? How is thermal comfort perceived? So all of that can only be done by data-driven calculations and science.
Yeah, the speed of that is obviously getting quicker and quicker as computing power becomes cheaper and cheaper. I mean, I remember back in the day, you might have run some of these simulations maybe once as part of a building control report, just to say, yeah, we've done it. It doesn't exceed some of the expectations. Whereas now, I guess it's much more iterative, isn't it? You can run those simulations that much more quickly and feed it back into the design. I think that's a big shift that we've seen over the last few years.
Yeah, completely. And there are a couple of softwares that enable us that integration and that iteration. So we use Grasshopper, and within Grasshopper we use tools that they are called Ladybug and Honeybee, that enables us to simulate, for instance, different facade parameters like the window U value and G value, the window size, the characteristics of the wall, different orientations, all of that combined in one go. So you simulated them in maybe like a whole day, and then you got the best performing combination of all those different factors. Years ago, that would take days of work. Now we can do it much quicker because there's a technical capacity and software availability, which is ready for us.
Yeah, so we're going to come back to that because I want to talk about that on specific projects like the Forge. But just working through some of these terms, perhaps you can talk about passive house, because I hear it used quite a lot, and I'm not sure it's completely well understood out of the industry.
Yes, I think there's a growing interest in passive house. Passive house is a standard for low energy buildings that was born in Germany. And I think it's quite well established in Europe in general. And I think it's picking up in the UK. And I've noticed that we've been preparing an article about passive house. And in doing that, I realized that there's a growing interest in the UK. And there's a heated debate about its suitability to achieve net zero carbon buildings, which I will explain in a second. But essentially, just to explain what it does, passive house asks you for very specific performance targets. One of them is to achieve a heating energy demand of less than 15 kilowatt hours per square meter per year, which is really low. For people who are not familiar with kilowatt hours, is a really low energy demand. Then it asks you to have a good overheating performance, to try to avoid overheating. And if you have a cooling system, it also has to be low energy. And then the characteristic that defines it the most is that its airtightness is really low. So that means that there's no air leakage through its envelope. It's almost thermal breach free. And that makes a really airtight building that doesn't lose any heat. So there are multiple benefits from passive house. The main one is that it's a well-recognized mark that achieves really low or ultra low energy and carbon performance. But there are other benefits. One is that the occupant's experience or perception is really good because the air quality is high because you have a heat recovery system that feeds fresh air. So the air is constantly being replenished. But also the temperature levels are really good, so you don't experience overheating. Now, there are challenges to passive house. One is that because it requires this very airtight envelope, additional insulation, additional overlaps of membranes to create that airtightness, it's more design. It's more expensive to design it, but it's more expensive to build it. And there's also some skill shortage. So you don't find many contractors that can design easily or comfortably a passive house building. And that creates a bit of a problem. The good thing or the good news for us is that because we are specialized in platforms and DfMA, that's a really good solution to these challenges because the complexity of the facade design can be resolved by platforms, which platforms in its essence tries to simplify the structure and the facade design, basically all the different assemblies, and that simplifies the design, simplifies the cost, reduces the program. And probably you can explain this better than me, Jaimie, because you're a specialist in the field. But one of the key aspects is that it facilitates that the labor can learn the methodology to build it, so that the skills shortage problem disappears. So yeah, that's a really interesting view at using DfMA to resolve these challenges in passive house.
Yeah, one of the key things about platforms is trying to get kind of manufacturing industry levels of quality into construction, and normally those things are poles apart. So we work with much higher tolerances in construction, whereas platforms are trying to get much closer to zero tolerance if we can get away from it. And yeah, that would instantly kind of help with things like air tightness. You made a point that I think is quite interesting about the user experience. So it's now defunct, but things like Code for Sustainable Homes, one of the criticisms was it encourages tiny windows and therefore, very stuffy buildings. You make them so airtight with so little glazing to prevent overheating that actually it's sort of headed towards these sort of dark, dingy spaces. But passive house doesn't lead you in that direction. So yeah, what it does in terms of design, I think is quite an interesting thing to expand upon.
Yeah, definitely. So when you do a passive house design, one of the things that you need to look into is overheating. And it is true that building regulations and some of the standards in the UK to design sustainable residential buildings mainly, they can create sometimes an overheating problem. But that's addressed by the passive house approach. One of the things I mentioned before, I don't want to forget about, is that there's a heated debate about passive house, which is, there's a lot of pressure to design net zero carbon buildings. And one thing that passive house does really well is designing net zero buildings in operation. So basically be net zero when related to heating, cooling, lighting, the operational side of things. But passive house doesn't really care about what happens with embodied carbon. So the criticism from some people comes, or their view is that passive house doesn't do anything about it, so it's not the right approach. But some other people say that actually passive house doesn't really affect the possibility of making a low carbon building from an embodied carbon point of view. So one thing that we've been doing in the building physics and sustainability team is doing a calculation to try to understand the truth and the technical and the reasoning behind this. And what is interesting is that it is true that if you have a passive house, you have triple glazing and an MVHR, a heat pump, additional insulation. And that increases the carbon or the embodied carbon of a building. But at the same time, you have a reduced boiler size, you have reduced number of radiators, you have a reduced size of PV arrays, and you have a compact shape. By having a compact shape, you have less materials. So we did a detailed calculation of this, and in total, the embodied carbon compared to a typical building was reduced by 0.7, which is virtually zero. So that means that you don't win, you don't lose. Effectively, you have a normal building from a point of view of embodied carbon. You can make it low carbon by just incorporating all the other measures you would put into any other building. Like you would look into the specifications, try to use timber, try to use low carbon steel, try to use low carbon concrete, and try to make it as close to zero as possible. So from my point of view, passive house is a good way to achieve a net zero carbon building from an operational point of view and also from an embodied carbon point of view.
Yeah, it was interesting. You talked about it starts with the sort of design process heading towards it, which is, we've talked lots on this podcast before about, it's the same with design for manufacturing assembly or MMC. It kind of starts with the design process. You don't post-apply this. It's quite embedded in the design process. So in that sense, it's quite aligned, isn't it, with the kind of aspirations of MMC? You're sort of heading in the same direction, or it's another one of these things which is pointing in the same direction, sort of overall better building performance.
Yeah, definitely. I think there are lots of synergies with between DfMA, modern methods of construction, and try to make more sustainable buildings. And I think one of the key discussions in the sustainability industry at the moment is net zero carbon in general. And I think there are lots of possibilities from DfMA and modern methods of construction to make it more, to reduce embodied carbon and operational carbon. I think there's a growing pressure because, as you probably know, the built environment is around 40% of the UK's total carbon footprint. And there are bodies like LETI or RIBA or the UK GBC who are leading the discussion and try to bring net zero carbon discussion to the center of the agenda. And there's even a project to make a new building regulations item, which is part Z, I think, to try to calculate embodied carbon. It doesn't exist at the moment, but I think its target is for 2030. So there's clearly a direction and a lot of pressure to reduce carbon, and I think it's feasible. I think it is feasible in the long term if you use things such as carbon offsetting schemes and power purchase agreements. But I think it's probably important to explain that nowadays, with just design means, so within the constraints of a building, it is very difficult to make a net zero carbon building. So what tends to happen is that you first try to reduce embodied carbon via design means, and then on the operational side, you need to pay to use renewable electricity. And on the embodied carbon side of things, you need to look for a carbon offset scheme and again, pay for that. And the quantums can be substantial. So when you look at, let's say, like a tower building or like a 20,000 square meter building, you can be talking about a couple of millions of pounds to offset all that amount of carbon. So it is possible. It is desirable, but it can be expensive if you leave the design decisions the last time of the design process.
Is it fair that net zero carbon people are generally, at the moment, they're more focused on the operational carbon? They're less focused on embodied carbon because it seems to still be quite hard to calculate. The data's not necessarily there. Is that fair, or has it moved on?
I think it has moved. I think traditionally, yes, there's been definitely a lot of knowledge in terms of energy simulation and carbon simulation in operation. And the industry has been growing over the last, I would say, 3 years in terms of the capabilities of professionals, but also the softwares available to calculate embodied carbon. And the industry, I think, has pushed in this direction. And nowadays, I think most architectural or building services engineers firms, they have an expert or a person who can estimate to a certain degree embodied carbon. Now, it is true that there's some data missing. One particular part of the data is MEP. So building services, there's not a lot of information. And that's one of the key challenges when you want to design, when you want to calculate embodied carbon. So we have lots of data about all sorts of materials, but not MEP items. And it's not a negligible quantity. Typically, the MEP embodied carbon of a building would be 15%. So if you don't calculate that, you're missing a big part of the puzzle. But I think in general, yes, there's a growing knowledge and interest in embodied carbon in the industry.
And also, it seems to you need to know quite a lot about the building that's quite specific. So travel distance of materials, so where you're sourcing the materials, where you're deploying them. Again, all of that makes it more complicated because you can't just model the building. You also have to think quite a lot about the construction process, the procurement process, all of those things. So that seems to also make it more complex or more building specific maybe than some of the other parts that you might do.
It is. And luckily, there are a couple of softwares available that simplify all that complexity because they have the right database and it's arranged in a way that it already includes assumptions for transportation distance, or for the amount of waste generated, or to what happens at the end of the lifetime of a building in terms of whether the materials are disposed to a landfill or they're recycled, etc. But what some of the leaders in the industry are trying to do, and that's something that we have done as well, is developing our own in-house tools. So we use third-party verified softwares, but we also have a tool that can go into a lot of detail into those details. Like we can refine the transportation distance, we can refine the amount of waste generated, we can refine the material use, and that's really important for us because since we are specialized in design for manufacture and assembly, one of the things that we need to do is try to quantify the detail of how much transportation we are eliminating because we are assembling components somewhere else, or how much waste we are reducing because our buildings they are much more refined, or whether there are opportunities to disassemble a building element, so that instead of going to the landfill, we can recuperate that material and reuse it for some other purpose. So we have that capability, and we have been developing it over the last few months and years. But it's true, it's complex, yeah.
And just to give a sense, have you got any examples of how significant waste and transport are, particularly in terms of overall embodied carbon? Is it a sort of couple of percent, or is it actually quite significant? Does it make a big difference?
It is not. It is true that, it is important to look at all the different aspects of the process. So just to give you a slide summary of how it normally works, you have the first part of the first phase of a whole building life cycle analysis is the manufacturing. And that could easily account or amount for 60% of the total. Then you have a second phase, which is the waste and transportation. That could be just 5%. It's not a lot, but when you're trying to push to net zero carbon, you want to address each single bit and piece so that you reduce embodied carbon. Then there's a third phase that has two small parts. One of them, it's really important, and it's one of my favorite topics about embodied carbon, which is the refrigerants. And I will explain a bit more about that in a second. And then there's the replacement. So in a building, all materials, they need to be replaced. Well, not all of them. Many of the materials, they need to be replaced. Steel and concrete, probably not, but all the finishes, they need to be replaced every 20 or 30 years or 10 years, depending on the material. MEP items, they need to be replaced every 20 years. And that means that they need to be remanufactured, installed again. So the amount of carbon over, let's say, 60 years adds up to a much bigger figure. And then the last part is the end of life part, which is when you quantify what happens if it goes to landfill, if you reuse it, if you burn it, etc. And just going back to the topic of refrigerants, because I think it's really important. When we talk about buildings, we always think about steel elements, the structure, the roofs, the foundations, etc. We can think about the MEP items, but most people forget about refrigerants because it's just what happens when the gas is released to the atmosphere. It doesn't seem too material, but it has a huge impact, especially in buildings which are heavily cooled, like a data center, for instance. You can expect that the refrigerant could have an impact of 15-20% of the total of embodied carbon. And that's a discussion that is becoming more important in the industry. The Safety Release TM65, which is a methodology to try to quantify the embodied carbon of MEP items. And they put a lot of stress in the impact of refrigerants because it's really high. So we need to, when we design building systems, we need to look into what refrigerants we use, because they can have a really high impact in the total of the whole life cycle of carbon of a building.
And presumably that's going to have a sort of big impact on how we design buildings. So particularly data centers, they're only becoming more prevalent
Yes.
Certainly, lockdowns taught us that reliance on good data infrastructure is becoming more important. So have you got any sort of thoughts on where that's going to start to lead us in terms of the design of some of these sort of very energy intensive building types?
Yes, I think one of the key aspects is that when you design a refrigerant with a low global warming potential, that has a knock-on effect. The first one is that the efficiency of the cooling system drops, which means that you either have to have more chillers and more equipment, essentially. So that increases the embodied carbon on the other side, and that also affects the design of the plant room. That can mean that the size is bigger. So that there are knock-on effects on the architectural design as well in terms of space planning. And one of the downsides as well is that apparently the refrigerants that have a lower global warming potential, they are more subject to burn. So, and I know that, we all know that in the industry now, fire protection is a sensitive subject. So we need to be also aware of that. But I think one of the smart way to address it is to try to find ways to create free cooling opportunities, looking at maybe thermal labyrinths, pre-cooling overnight, using thermal mass, any kind of means to try to reduce the active cooling and try to facilitate, if possible, a passive cooling or free cooling.
Yeah, which then leads on to material choice. So one of the things I was really keen to talk about, I know we've spoken about it previously, is the ongoing steel versus concrete versus timber debate. So I know there's a sort of knee-jerk thing that says, well, timber must be the right answer, but it's a lot more complex than that, isn't it? Perhaps you can unpack that a bit.
It is complex. It is slightly controversial because I think when you open any newspaper, there are always news about sustainability and construction, and you can see lots of articles talking about timber constructions, like if it was a holy grail, like if it was the right solution, but it's actually complicated. So concrete, it is true that concrete has accumulated for most of the embodied carbon emissions over the last decades because it's a material that is carbon intensive. But the positive thing of concrete is that probably due to that ongoing pressure, the industry has been shifting and releasing products that have lower carbon, not low carbon, which is something that still, at least in the UK, cannot do yet. So steel is really carbon intensive. That's partially due to the process to manufacture it. And the way to reduce it would be to use electric arc furnaces, which are fed by renewable energy, if possible, and increasing the percentage of recycled content. But that's not available in the UK. So you need to source it from Europe and complicates things. So that means that we need to wait probably a decade, or I don't know for how long, but probably for a long time until the whole industry, the steel industry, gets up to speed in the UK when it comes to low carbon materials. And I think concrete has been faster on that. Now, when it comes to timber, yes, timber captures carbon. But what most people don't talk about is what happens at the end of the lifetime of a building. So just to explain you the process of how timber captures carbon. When a tree grows, obviously captures carbon in its different parts of its body. Then you cut it because you don't use the branches, the leaves, and the roots. So you probably release 50% of its carbon emissions when you chop a tree. And you're using just half of it. And that's stored in your timber beams and columns and floors, etc., until you demolish your building. And that time, different things can happen. If you release the timber into a landfill, it releases carbon, so you lose the positive benefit. But it also releases methane. And methane it has a much higher global warming potential impact than carbon. So it has a really negative impact. Now, there are ways to attenuate that. One is that in some landfills, you can actually capture the carbon. So there are ways to do it. And the most efficient or the best way to do it would be to take that timber and reuse it. So that puts a lot of pressure on the design. We need to design for buildings that get dismantled easily and that can reuse the material for future projects. But it's easier said than done. So one of the challenges is that as architects, I think we can do it. But clients, they need to be on the same line. They need to be clear about whether they can have the capacity so that in 60 years' time, they can say, well, I'm going to demolish my buildings, but these pieces, they're going to be used in a different way. That's really difficult to say. It's a really difficult commitment for a client. So that completely dismantles potentially the benefit of timber. There are other sides of the discussion. Sorry, I'm maybe understanding a lot of this, but I think it's important to explain that timber has some fire implications. It has some MEP implications of coordination because you have downstand beams that they are deeper. So you can coordinate a concrete slab or a frame with a steel frame slab easier, probably. And there are also the things that people don't talk about, which is that timber releases volatile organic compounds, which are bad for your health. And that's something that doesn't happen with steel and concrete. And one of the things is that timber is a light material. Concrete has thermal mass. We know that thermal mass has lots of benefits in terms of thermal comfort. So the equation is complex. It's not a simple discussion. So you need to account for many things. And it's not like timber is better. Well, it depends. Concrete can be better than timber, and steel can be better than timber, depending on the characteristics and the specifications of those two materials.
Yeah, in my head, it feels like all these things, they're all very complex. We need a rich mix of things moving forward. It feels like the route to low carbon concrete is much quicker than steel. Yes. I mean, all of the big steel manufacturers seem to be on the path of electric arc furnaces, but it feels like that's quite a way off. It feels like there's quite a lot of technology for concrete that's on the starting blocks, and it feels like timber's a very good interim while we get there. Could we get to the point where concrete makes more sense sustainably than timber, or do you think timber will always have an edge if we can sort out sequestration?
I think if we solve the sequestration and the carbon capture, it will always have the edge. But that's a big problem. I think in the meantime, we can reduce embodied carbon from concrete by a big proportion to the degree that it can compete with some timber structures and with the best of steel structures. So I think when we look at embodied carbon, we need to look at on a project basis. We cannot say that steel is better than timber or concrete is better than steel. We need to look into the characteristics of the building, the grid of the building, things such as MEP coordination, any potential problems of overheating. Take all of that in the equation and say, okay, I think probably makes sense to go down this route and select this material.
Yeah. The other thing, I mean, no one's ever answered this question to my satisfaction. Do we know how much timber's available to build with? I've got an inkling that you go, I bet we couldn't grow enough timber to make every building we ever need. But I don't know whether that's just a completely, that's just my perception, or whether anyone's actually looked at it properly, or where is it going to come from? We can't grow necessarily as much in the UK as we'd need. I don't know if you know any.
No, I will leave you disappointed, unfortunately. I don't know the answer. So, and that's actually a really complex subject, because you need to, the right way to do it is to source timber is to source them from sustainable sources. And not all the forests in the world, they are certified. And that already limits the amount of timber that you have. But it is true that if all the buildings in the world, they decided to be built in timber, I don't think there would be enough timber. And on one hand, we need to look at how we make buildings which are more sustainable, but at the same time, we need to allow for forests to grow. I think there's a growing pressure in the sustainability debate to increase the mass of trees, and we cannot just fight in the opposite direction. So there are side effects like the impact on ecosystems and the global climate balance of the different countries, etc. So it is complex, and I don't have the clear answer. But I also think that we cannot build all the buildings with timber in one go. There's no enough timber, probably.
Yeah, no, okay. So, only slightly more. If anyone's listening and has any answers or knows of any research that's been done, we'd love to hear from you, because this it's a huge topic, isn't it? And we could talk about this all day, but just that complexity between those three material types is, there's so many unanswered questions, and it's such a tricky thing to get your head around. But the industry needs to get some answers to these questions fairly quickly, doesn't it? So any pointers will be gladly received. So moving on a bit, so we've talked a bit about the Forge, certainly in this podcast, we've touched on it. That is UK's first net zero commercial building. We're delivering it for Landsec at the moment. It's the first project using platforms. Perhaps you can talk a bit about the design process and the metrics we're getting on that building, and what that means in terms of net zero, how that's being achieved, etc.
Yeah. So yeah, as you said, it's the first commercial building in the UK to align with the UK GBC framework for net zero carbon. And that means that it is net zero in operation and is net zero from an embodied carbon point of view. And that's important to highlight because there are many buildings out there that claim to be net zero, but they are just net zero of one part of the equation, regulated energy only, or sometimes the whole operational energy. But I don't think there's any commercial building. This will be the first one in the UK to cover the whole spectrum. And one of the reasons, and one of the things that we did to achieve a low carbon building, and then do further steps to become net zero, is to adopt neighbors' design for performance scheme, which for people who are not familiar with it, you probably will know that in the UK, we use Partel to calculate carbon emissions of the regulated side of the energy. But there's a well-known and established knowledge that Partel doesn't define very well how the building operates. There's a performance gap. So there are other schemes such as CIPSI, TM54, and now neighbors that try to define the performance of buildings in a more accurate way. In doing so, what tends to happen is that the more accurate you are, the more carbon emissions you calculate or you estimate, the more energy intensive your buildings become, because you're close in the gap to how buildings operate. And that means that you need to reduce more carbon, you need to reduce more energy, and it's a bit more challenging and requires more work. And that's something that we have done for neighbors. We are pioneers in neighbors. We are advocates of neighbors. We want more buildings to be done using this neighbors scheme because it's more accurate and it's more representative of the performance. And in doing that, we have reduced the energy, not just of the small parts that are addressed by building regulations, but we have looked into the lifts, the IT equipment, each single part, each single bits and piece from the energy consumption of the building. That has made a huge difference. Now, the embodied carbon side of things, the greatest achievement is that when we started with the calculation that we did in coordination and collaboration with Candles, is that we reduced 19.5% of the embodied carbon by using DfMA. That's a lot. That's a lot of carbon just by using a platforms-based approach. And it's great news for us. It's great news for the industry in general because it shows that it can be done and that has a lot of benefits. And then once we did that, the design evolved and we kept on looking at specifications and other ways of reducing embodied carbon, and we reduced from 19.4 to 24%, which is quite a lot. So what happened after that is that, as I mentioned before, when you try to push to reduce embodied and operational carbon, and then you need to use a power purchase agreement, which is renewable energy, and pay to offset. So that was the last part, so that we can claim that the building is net zero carbon. And there are lots of interesting, exciting strategies that we put in place to reduce carbon. I think that the general concept is that this is a lean design. So in using DfMA, we have tried to simplify the structure. We have tried to simplify the facade, the frame. We have eliminated suspended ceilings in most of the spaces in the building. They are not needed. So basically, the design approach is eliminate what is not needed. If you eliminate it, you reduce carbon from design. And we have looked at then ways to be low carbon by selecting concrete that has a percentage of cement replacement. So basically, you're eliminating cement by using other material. In this case, it's called GGBS. And we have looked at what if we use recycled, reclaimed raised floors. There's a lot of, because it's an office building, there's a lot of raised floor surface. So we are using reclaimed raised floor that reduces carbon by quite a lot. And other important strategy is that the building is designed for the construction. As I was mentioning before, it is important that the buildings can be disassembled so that rather than throwing things to the landfill, you can reuse it for some other purpose in the future. And then from the operational side of things, so there are a few lessons learned from this building. The first one, probably one of the most important, is that neighbors creates a huge opportunity for us to close the performance gap. Another one is that the concrete that was originally specified is a self-compacting concrete. And a self-compacting concrete is more carbon intensive. So what we did to try to compensate it is using GGBS or another cement replacement. But we need to find opportunities to avoid using self-compacting concrete if possible. And that's one challenge that we need to address as designers. Another interesting thing to look into in general is that when you design aluminium elements, if you use powder-coated aluminium, it is less carbon intensive than a conventional anodized aluminium, and that's what we have used for some elements of the facade. And I think one really important thing to always look into is the importance of sourcing. So in the structural approach, we have some microcolumns, which they are tubular in shape, and they are EU sourced. So I think it's a bit more complicated to source this from the UK. But in sourcing them from Europe, the percentage of recycled content is lower. In the UK, you can start assuming that it's 20%. In Europe, is 0. So if you source certain steel materials from the UK, you have an edge on that. And aluminium, in this case, many of the aluminium materials that we specified, they came from Poland. And Poland depends a lot on coal, which means that the embodied carbon of all the materials, they are always more carbon intensive. So it is better to look into other countries for your aluminium. So there's always something you learn about it. And in the Forge, there are lots of interesting lessons learned.
I mean, those numbers, 24% reduction in embodied carbon, that's a huge step forwards. But what you're saying is over time, obviously, one of the benefits of platforms is you continue to refine them, you continue to get these things to be better and better. So, yeah, we'd hope those figures improve. One of the things you mentioned was offsetting, but you need to do that almost as a last resort. I guess people might think, I can just offset this, but you go, well, there's only limited capacity in the grid for offsetting. Not everyone can do it. You want to do that, almost as a kind of last resort. Once you've designed out as many of these things you possibly can to try and limit that pressure on the offsetting part of the grid. Is that right?
I completely agree. And I think one of the reasons is first, you need to be honest about your design. So you need to design buildings which are as low carbon as possible within the possibilities of its design. And only then you offset. That will make your project a bit more honest from my point of view, from a carbon point of view. But also at the same time, when you offset, you need to pay. And as I mentioned before, the quantities that you need to pay, they are not negligible. You can be talking for a large project, you can be talking about millions. So when clients hear that you design a building and you don't care about reducing measures, and all of a sudden you come with the figure, hey, by the way, you need to pay £2 million, that's obviously not good news. And the carbon prices are increasing and are likely to increase. So yes, probably you don't want to give that kind of bad news to a client. You want to reduce the embodied carbon emissions and operational carbon emissions from design opportunities, which are free, essentially.
So it's fair to say for clients listening that it's better to spend more money on design and less on offsetting. Just saying. Perfect. Just conscious of time now. We need to, I guess, wrap up quickly. But we always like to ask guests what their sort of view of the industry looks like over the next sort of 5-10 years. Obviously, it feels like we've made big inroads with the Forge for all the reasons you've talked about. There's a obviously growing acceleration of interest in this topic. The data's getting better, the software's getting better. Where do you think we could be in 5-10 years towards sort of making some really big inroads into dramatically reducing embodied carbon and operational carbon in the built environment?
I'm optimistic in general as a person, but I'm optimistic in also about the industry because there are lots of people pushing in the same direction. You can see lots of buildings which are fighting to get the right headline, like this is the first building that is net zero, or my building has reduced this amount of carbon emissions in operation. And there's a true fight by clients to be at the leading the game, essentially. And I think there are lots of bodies like GLA, LETI, RIBA who are pushing the same direction. Building regulations are changing in the right direction, although they could push a bit more. I think that's what most people think. And so from that point of view, I'm optimistic. And I think in 5 years' time, designing net zero buildings will be quite common. And hopefully in 10 years' time, we'll be talking about huge changes in the industry. One of the key differences that will completely change things is that the grid is being decarbonized, and that will affect the materials, that will affect the performance of the buildings. And that's good news in general. So in general, I'm optimistic, although when you look at the outside world, things related to global warming are a bit less optimistic and problematic, but that's, I guess, a different story.
But it's needed as a stark reminder, isn't it? We have to get this to be business as usual. We have to move beyond the kind of, the nations first, the world's first, and into the kind of, almost needs to be a strange event if someone doesn't or designs a building that isn't net carbon zero. That's where we need to get fairly quickly, isn't it?
Yeah, absolutely. I think we need to do our part in the construction industry. There are lots of different actors when it comes to reducing the impacts of global warming, and we need to do our fair bit.
That's great. That's probably all we've got time for. So we'll have to wrap up there. We could obviously have talked about this for a lot longer, but as I say, if anyone's got any further insights, further research that we can have a look at, then we'd love to hear from you. So Pablo, thanks ever so much for joining me, and enjoy the rest of your day.
Thank you very much.
So thanks ever so much for listening in, and please join us next time for more Built Environment Matters.
Thank you for listening to Built Environment Matters, a podcast brought to you by Bryden Wood. Listen and subscribe wherever you get your favourite podcast, and you can follow Bryden Wood on LinkedIn and Twitter.